So in this video, we'll be learning about the Taylor series and how can we use it. So we have, let's say, f of x, and the general formula states that we can write any function in terms of sum of infinite number of polynomials. So it is equal to sigma of n is equal to 0 all the way to infinity. And we have, now it's the tricky part, f of n. I'm going to explain each term after writing the formula, so don't worry about that. At a value over n factorial multiplied by x minus a to the power of n, where a will be given in the question and it is the center. So now what is f of n? N here is actually the nth term derivative. So here, if n here is the first term will be n is equal to 0, right? So f of 0 at a value will be the function itself at the value of whatever a is equal to. Now if it is f of 1, it's going to be the first derivative at a value, and if it's the second, n is equal to 2, it's the second derivative, n is equal to 3, it's the third, and so on. So once we start doing examples, this will be more clear for you. Now one important thing to remember is in Taylor series we always start with n is equal to 0, because in the other one that we'll be doing in the next video it will start with 1. And the other thing is, of course, f of n here is the nth term derivative, so keep that in mind. And now let's start with some examples. So I just wrote the formula at the side so you guys remember. So we need to find the Taylor series of the function f of x is equal to 1 over x at a is equal to 2. So let's start with writing that 1 over x is equal to series of n is equal to 0 all the way to infinity, and we have f of n at 2, because a is equal to 2, over n factorial multiplied by x minus 2 to the power of n. So now let's expand this and start substituting the n's. So when n is equal to 0, it will be the first original term, so f, the function itself, at 2. So this is what I mean by the nth term derivative, because n is 0, so it will be the original function at x is equal to 2. So I'm just going to write f of 2 right for now and simplify it later, over n factorial, which is 0 factorial, multiplied by x minus 2 to the power of 0. So now let's continue when n is equal to 1. So it will be f prime, because n is equal to 1, so f of 1 is the first derivative. So f prime of 2 over 1 factorial multiplied by x minus 2 to the power of 1. Now when n is equal to 2, we have f prime prime double prime at the value of 2 over 2 factorial multiplied by x minus 2 to the power of 2. And let's write the third one also. It will be can I fit it over here, f triple prime of 2 over 3 factorial multiplied by x minus 2 to the power of 3. So now normally in your exams your teachers will ask you the first 4 or 5 terms. So this is when you just stop, because this series goes until n is equal to infinity, right? So it never ends. So now we need to evaluate all of these numerators. So I'm going to do it on the side. So let me just scroll down a little bit. When n is equal to 0, we have f of x as the 0 nth, the 0 derivative. So it's just going to be f of prime, which is evaluated at x is equal to 2, since we have f of 2, and that'll be 1 over 2, right? Because we had the function of 1 over x, and you just substitute x as 2. Now, when you have n is equal to 1, we have f prime of x. So what is the derivative of 1 over x? It's going to be negative 1 over x squared evaluated at x is equal to 2, and this will be equal to negative 1 over 2 squared. And you'll see why I'm not simplifying this later. So leave it as this, the x to the power of 2, so it's going to be 2 to the power of 2. Now when n is equal to 2, we have f double prime of x, which is equal to, if we bring this x above, so it's going to be negative x negative 2. So let's bring this down, so it will be positive 2 over x negative 3, and then you bring it down, so it's going to be 2 over x cube as your function for f double prime. So 2 over x cube, and evaluated at x is equal to 2, so we will get 2 over 2 cube. So now when n is equal to 3, I'm going to write it over here since I don't have that much space. We have f triple prime of x here, and f triple prime is going to be negative 6 over x to the power of 4, which is evaluated at x is equal to 2, so we'll get negative 6 over 2 to the power of 4. So now instead of erasing our previous equation, I'm going to substitute all the f of f prime and all these functions. So f of 2 was 1 over 2, so let's erase this part and replace it with 1 over 2, and I'm going to bring the denominator below. And then the next one is f prime of 2, which was negative 1 over 2 squared, so 2 squared goes down, or actually let me put the brackets on this one first. So f double prime is 2 to the power 2 over 2 to the power of 3, so 2 and then 2 to the power of 3 here, and then f triple prime was negative 6 over 2 to the power of 4, so negative 6 and then 2 to the power of 4. So now I'm gonna write this in a more clear manner so that you guys can understand. So now what we want to do is write a formula which can write a series which can show us this pattern. So we have series of n is equal to 0 all the way to infinity, and we need to now slowly step by step write this sequence. So the first thing that we notice is the sign is alternating, plus minus, because is minus 1 and then 2 negative 6. So the first thing that we can do is write negative 1 to the power of n over, now we see that we have 1 over 2, negative 1, I'm going to ignore the sign for now, so 1 over 2 squared, and then we have 2 over 2 to the power of 3, and then negative 6 over 2 to the power of 4. So here we have 2 to the power of n plus 1, and you might be wondering why do we plus 1 over here, because if we take 2 to the power of n, it's actually 2 to the power of 0, and that is not our first term, it's 2, right? So we need 2 to the power of 1, so that has to be n plus 1. Another thing that we can notice is we are multiplying it by x minus 2 to the power of n, so here we can just include that. And another thing that we notice is we have 0 factorial, 1 factorial, 2 factorial, 3 factorial, so we here need n factorial, right? Now there is one last thing that we notice. We have in the numerator 1 and then negative 2, negative 1 and then 2 and then negative 6. So what pattern is this behavior? And actually ignore the sign for now because we already took care of the sign. This here is 0 factorial, this is 1 factorial, 2 factorial, 3 factorial. So we have another n factorial in the numerator. So here we have n factorial in the numerator, and we can use that to cancel the 1 in the denominator. And another thing that you might notice now is, why did we not simplify the derivative when we had 2 to the power of something? Here, that is the main thing why we noticed to write this 2 to the power of n plus 1. And here is the final Taylor series for this question. So now we'll be looking at it in another formula which evaluates the Taylor series when a is equal to 0. So we're just going to substitute whenever we see a with 0. So this formula is called Maclaurin series, and it's the same formula as Taylor series, except that a is going to be 0. So f of n derivative of 0 evaluated at 0 over n factorial multiplied by x to the power of n, because a here is 0, and this is called Maclaurin series. So basically in Taylor series a is not equal to 0, and in Maclaurin series a is equal to 0. So now let's do some examples. So this is our second question, which is f of x is equal to e to the power of x, and we are to evaluate this at x is equal to 0, which means that we need to use the Maclaurin formula here, where a here is equal to 0. So let's write the formula. E of e to the power of x is equal to sigma of n is equal to 0 all the way to infinity, f of n term derivative at 0 over n factorial multiplied by x to the power of n. So now let's expand this. It will be equal to the first term. When n is equal to 0, it will be f of 0 derivative multiplied at 0 actually. So f of 0 is just the term itself. So I'm just going to write f of 0 over 0 factorial multiplied by x to the power of 0. Now the first term when n is equal to 1 will be the first derivative, so f prime at 0 over 1 factorial multiplied by x to the power of 1. Now double derivative of f double prime evaluated at 0 again over 2 factorial multiplied by x squared. Now the third one will be when n is equal to 3, f triple prime at 0 over 3 factorial multiplied by x to the power of 3. And normally questions, again I'm repeating this, will just ask you to have the first 3 or 4 terms, and that's it. So here we did our first 4 terms, so that's enough. So now we need to find the derivative at 0. So let's start with that. When n is equal to 0, f of x is equal to e to the power of x, since it's the 0 term and that's the function itself, and if we put x as 0, is going to be e to the power of 0, which is equal to 1. Next, when n is equal to 1, what is the derivative of e to the power of x? That is going to be e to the power of x again, because it stays the same. So you need to also know your normal and common derivatives, the basic ones, which is e to the power 0 again and 1. So if you notice here, when we are increasing it, and 2 and 3, is the function is going to stay the same. F double prime is going to be the same, and then is going to be e to the power of 0 again, and it's going to be equal to 1 even for this one. So now let's replace our functions with the values that we got. So we got 1 for all of them. So oops, no, that's the wrong one. Let me go back. Yes, starting from here, 1 1 1, and then the last one, 1. And we can erase this now. So now we need to somehow come up with a formula or a series which for any n term would give us the correct answer. So sigma n is equal to 0 all the way to infinity. So what do you suggest here? We have a 1 in the numerator for all the answers, all the terms, so there has to be 1 in the numerator. And we can notice that we have 0 factorial, 1 factorial, 2 factorial. So here we would have n factorial for sure, and then multiplied it by x to the power of n, since we have x to the power 0, x to the power 1, 2, 3. So in this question, we actually got lucky with the function, since all of the derivatives were equal to 1, but some of the functions could be very complex, and finding the formula which suits all of the terms of n could be very difficult, and we'll be having a lot of examples. So yeah. And your final answer here is this part, which is the Taylor series, or you can say Maclaurin, it's the same thing. So now our next example is going to be with trig function. So I need your full attention, since this is a complex question. So we have f of x is equal to 5 cosine pi x at x is equal to 0. So let's write the formula. We have 5 cosine pi x at sigma of n is equal to 0, f of n term at 0 over n factorial multiplied by x of n. So the first thing that we notice is there is a 5, which we can just remove it for now and multiply it by this series later onwards, because it will be more simpler to find the derivatives and all that. So let's first now find the derivatives for f of n. So the first one, when n is equal to 0, we have f of x is equal to cosine of pi x evaluated at x is equal to 0, which is equal to 1. Now when n is equal to 1, we need to find f prime of x, which is going to be equal to negative pi sine of pi x at x is equal to 0. This will give us 0. So this is a very important thing, and I need your full focus and attention here. Now whenever we get 0 as our functions, we need to ignore that n. So for now I'm going to write all of them, and then I'll tell you what do we do with them. So when n is equal to 2, this is f double prime of x, which is negative pi squared cosine of pi x evaluated at x is equal to 0, which will give us negative pi squared. So now let's, okay, there's one more, and then we'll start writing it. F triple prime of x, which will be also equal to 0. So now let's start writing it. So we have the first one, which is 1 over 0 factorial multiplied by x to the power 0, plus we have 0 over 1 factorial multiplied by x to the power 1. So what I mean to say is, whenever you have a 0 as one of the terms, you ignore them, and you don't count them as your first or second term, you just ignore them. So that's what I'm going to do. I'm going to jump next term which has a value. So next one is negative pi squared over 2 factorial multiplied by x to the power of 2. And when you have n3, that is also equal to 0, so we ignore that again, and to find the next one. So when n is equal to 4, we still need to find our first 4 terms, by the way. So you skip the ones which are zeros, and you only take the ones which are having a value. So when n is equal to 4, I'm going to erase this part over here so we have more space. yes. So when n is equal to 4, we have f4 primes, which will be equal to pi to the power of 4. And when we find n is equal to 5, it's going to be 0. So we need to find the next one, which is n equal to 6, which will be equal to negative pi to the power of 6. So if you can see the pattern here, we are just multiplying it by negative pi squared every single time, every two terms. So here we just multiplied 1 by negative pi squared, and then again, so we get pi to the power of 4, and then one more time. So let's write that now. It's going to be pi to the power of 4 over 4 factorial multiplied by x to the power of 4, and the next term is negative pi to the power of 6 multiplied by x to the power of 6 over 6 factorial. So here we have our first 4 terms, and now we can start writing the series which shows this pattern. So sigma of n is equal to 0 all the way to pi. The first thing that we notice is we are alternating the sign each time. So positive, negative, positive, negative. So we need negative 1 to the power of n. Now another thing that we notice in our sequence is that we have pi. So we need somehow to have pi squared multiplied every single time. So how can we do that? Let's write pi, and let's try with let's say 2n, because there is no pi over here when n is equal to 0. When we have n is equal to 1, we have 2. When we have n is equal to 2, we have 4. And then when n is equal to 3, we have 6. So this pattern shows that power. And we have the same behavior for the denominator over here. So I'm going to write 2n factorial multiplied by, don't forget the x, so x to the power of 2n, and we are done with this question. Oh, there is one last thing. Remember that we took out the 5, so we need to write this series multiplied by 5. And this behavior is common whenever we are having zeros as alternating in power. So let's do another question now. Question number 4 is f of x is equal to x to the power of 3 minus 2x plus 4 evaluated at x is equal to 0. So find your derivatives first. When n is equal to 0, the first original function, you substitute 0, you will get the answer as 4. When n is equal to 1, you just do the derivatives and you will get the answer as negative 2. N is equal to 2, you get the answer as 0. When n is equal to 3, we have the answer as 6. And let's now write the formula. So it's going to be, I'm going to simplify questions very quickly. It's going to be 4 over n factorial, which is 0 factorial, which is 1, multiplied by x to the power of 0, which is just 4. So I'm going to leave it as that. Next is negative 2 over 1 factorial multiplied by x to the power of 1. So that is going to be simplified to minus 2x. And next one is a 0, so we can just skip that. And the last one is 6. So plus 6 x to the power of 3 over 3 factorial, which cancels out the 6 with this one. And what do you notice over here? We got the same exact question as our answer, right? And the reason for that is because we started with a polynomial. Normally in all of our other questions, we did trig, we did exponential, e to the power of x, and so on. And in this question, we just took a polynomial, and his Taylor series is to convert a difficult question or function, which is difficult to integrate, differentiate, into a polynomial. And the reason why we did this example is to show you guys when we take a polynomial in our Taylor series, we get the exact same answer. So, for example, if we have question 5 as f of x is equal to x to the power x multiplied by e to the power of x, here, if we normally just apply Taylor series to the entire thing, we would have to derive this and use a product rule. And for f of triple prime, we would have to use our product rule 3 times, which is too long, and why are you complicating things that much? So here, what we could do simply is we could leave x as itself, as it's a polynomial, and just apply Taylor series to e to the power of x, and whatever series that we get in the end, just multiply that with x. And another example here, f of x is equal to x over x to minus 1. Here we would have to use quotient rule to derive this, and for again f double prime, f triple prime, we would have to use 2 times quotient rule over here, 3 times quotient rule. So it's just smarter to do it separately. So you can write this as x multiplied by 1 over x minus 1. This is a polynomial, this is a fraction, and just use Taylor series for this part. So now let's just do question 5. And if you guys remember, we did do an example of e to the power of x, and we just have an extra x over here. So let's write this as x to the power x multiplied by the series that we got from before. So we have n is equal to 0 all the way to infinity. We have 1 over n factorial multiplied by x to the power of n. And if you're wondering where I got this from, it is, I think, example number 2. Yeah, it's number 2, and we got the series. And all we have to do is multiply x with the series, and here we notice that we have x to the power of 1 n, and here we have x to the power of 1, and we can add that, and the final answer would be series of n is equal to 0 all the way to infinity, 1 over n factorial multiplied by x to the power of n plus 1, which is just basic exponential rules. If the base is the same and you're multiplying, you just add the powers, right? So we do this exact same thing, except that n is here, so n plus 1. So let's do question 6 now. F of x is equal to x squared minus 2 minus 1, over 2 minus 1 plus cosine of x at x is equal to 0. And as you guys remember that we did cosine in our last example, so let's write the answer. It's going to be x squared over 2 minus 1, and then the answer that we got for cosine was, in brackets, 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial plus, and if you guys see that we can cancel this 1 with this minus 1, and minus x squared over 2 factorial is equal to x squared over 2, so we can cancel this part with this part. So all we're left with is the sequence which follows after this. So now let's write the final thing. It's gonna be x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial plus x to the power of 8 over 8 factorial. I'm just expanding it so that we can write the series after this, x to the power of 10 over 10 factorial, and so on until infinity. So now we need to write a series which shows this pattern. So we have n is equal to 0, and the first thing that we can again notice is that the sign is alternating, plus minus plus minus. So right away we can write that negative 1 to the power of n. Now we notice that the power of x starts from 4, so this is a very important notice. So here I'm going to write x to the power of 4, and each time it is increasing by 2. So here we can do plus 2n over the denominator has the same logic as a power, so it's again 4 plus 2n, and the entire thing is under factorial. Don't forget that. Now let's do our last example, question 7, which is f of x is equal to x over 3 multiplied by ln of 1 plus x squared, close brackets. Now sometimes the most basic formulas of the Taylor series will be given to you in the exam. Even if it's not given to you, it's very easy to find them. Just do the formula and then you will find the series. So for example, for this question, the ln of 1 plus x was given to you as x minus x squared over 2 plus x cubed over 3 minus x to the power 4 over 4, and so on. And the only difference here with our question is that we have ln of 1 plus x cube instead of 1 plus x. So here, whenever we see x here, we can just replace it with x squared. So we would have x squared minus x squared squared over 2 plus x squared to the power of 3 over 3 minus x squared to the power of 4 over 4, and so on, right? So we can simplify this and write this as x to the power of 2 minus x to the power of 4 over 2 plus x to the power of 6 over 3 minus x to the power of 8 over 4. And we can write the formula as n is equal to 0, infinity. We have alternate signs, so first of all -1 to the power of n. And the next thing that we notice is how do we write the sequence or the formula for the x. So first of all, you notice that the first term is x squared, so you need to have a 2 anyways, and every single time when we increasing the n, it is becoming plus 2 plus 2 plus 2, so it should be 2 plus 2n. And we can try this, by the way. So when n is equal to 0, it will give you x squared. When n is equal to 1, it should give you x to the power 4, which it does. When n is equal to 3, it will give you 6. So that's right. Over, we have now, here we have 1 as a default when n is equal to 0. So we should have a 1 over here. And each time we are increasing by 1, so that is going to be n. Now don't forget that we did have x over 3 multiplied by this entire series. So if I make some space over here, you could write x over 3 multiplied by the series, and we notice that we do have an x over here. So what we can do here is we can just plus 1 to this series. So it's going to be 3 plus 2n, and we can get rid of this one, and we can leave the 1 over 3 outside. It doesn't really matter. So that's all for this video. If you have any questions about any of these questions, feel free to ask them in the comment section. I'll be more than happy to answer, and thanks for watching.